Hello everyone. In this video we'll discuss about some of the important effects of the optical phenomena. So when we say optical phenomena, here we are talking about the reflection and refraction mostly. So because of these phenomena, right, we'll see some practical effects, whether it is the rainbow formation or the scattering of the light. So various effects that we'll observe around us, we'll try to discuss in this video. Okay, so we'll start with the first one, which is when we look at the position of star in the sky, right, the real position is something that we would not be able to observe. So the apparent position of the star is something that we will be able to observe when we are viewing it from the surface of the earth. Okay, so why does it happen? Because if you look at the atmosphere as such, right, atmosphere will have different layers. Generally the arrangement of the atmosphere layers will be such that as we move up upper layers of atmosphere, obviously the physical density will be less, and same will be the case of the optical density also. So if we go to the higher layers of the atmosphere, the refractive index will be less. When we come to the lower layers of the atmosphere, refractive index will be high. So as a result, what happens is when the light ray from the star is passing through the layers of the atmosphere, what we'll see is that at each and every layer it will keep getting refracted. Refracted means what? Here it is moving from upper layers are what? Optically rarer, lower layers are optically denser, so that will keep moving towards the normal. The ray will keep moving more and more towards the normal, so it will be bending in such a way that the final observer who is on the surface of the earth, he would view that the light ray appear to come from a different position. So this is what we will generally refer to as the apparent position of the star. So here the refraction through the layers of the atmosphere, right, is the reason why we'll see a different position of the star. So we will not be able to see the true position of the star, but we will see the apparent position of the star, and generally the apparent position will be more closer to the normal at the point. So you can see if the observer location, we will draw normal, right. So if we draw normal to the observed location, what we see is that apparent position will be more closer to the normal at the point of observation. This happens because of the refraction through the layers of the atmosphere, and importantly the atmospheric layers will be arranged in such a way that the upper layers will be having they'll have of course lower physical density, but here physical density is not of importance for us. We look at what is the optical density. Optical density also, upper layers will be lesser optical density. As we keep coming below, the lower layers of the atmosphere will have higher optical density, so the ray will keep bending towards the normal. So this is how the path will be. It will keep bending towards the normal as it is coming to the lower layers. So thereby we will see a apparent position of the star, which will be more closer to the normal at the point of observation. Now the same thing will also happen for the sun, which is the reason why we'll have a greater visibility of the sun even when the sun is beyond the horizon point. Like say for example, what we normally expect is if the observer is stationed here, we'll expect that he will be able to view the sun when it is reaching the horizon point on the M, and the visibility will continue when the sun is reaching up to the point E. This is the other horizon point. But practically what happens is the person will be able to view the position of the sun even beyond the horizon point. Like say for example, if you look at the position of the sun here, this is below the horizon. Now the rays coming from the sun, they would keep getting refracted through the layers of the atmosphere. As you can see, there are the different layers of the atmosphere that are marked. Again here what is going to happen, the layers of the atmosphere, as we move from the upper layers to the lower layers, what is going to happen, the refractive index is going to increase. Now when we see the true position of the sun, which is below the horizon point, the rays coming from it will keep getting refracted and refraction, always the bending will be towards the normal, because we are coming from lower refractive index layers to the higher refractive index layers. So we will be able to see the position of the sun even before the sun has reached the horizon point. So the perceived position, right, will appear to be kind of higher than what is its true position. This will happen on both sides. Means we will be able to see the sun even before it has reached the horizon. We will be able to see the sun even if it has already crossed the horizon. Like even if it has crossed the horizon, we will be able to see it. Even if it has before reached the horizon, we will be able to see the sun. That is the reason why the visibility of the sun will be there even before the sun has reached the horizon point, and it will continue even after the sun has crossed the horizon point. Okay, so this is also because of the refraction through the layers of the atmosphere. Now the other phenomena that we will see with regard to the stars is twinkling of the stars. I'm sure a lot of us will observe it. If you look at the sky in the night, what we'll see that there will be twinkling of the star. For a moment it will appear to be very bright, and then the next moment it will appear to be dull, almost invisible kind of a thing. So why does this twinkling of the stars happen? Again, the reason is in the refraction through the layers of the atmosphere. Like remember, already we talked about this refraction of the light coming from the star through the layers of the atmosphere. Now if this is a fixed arrangement of layers, if it is a fixed arrangement of layers, what we'll expect? We'll expect that the apparent position of the star will be shifted by a particular value, some angular shift. But the thing is, the composition of the atmosphere is kind of dynamic. So you'll have the air currents, you'll have the other phenomena happening which will keep changing the composition of the layers. As a result of it, what happens is the fluctuations happening in the atmospheric layers, right? The refractive index of the atmosphere will keep changing. So we'll see that the refractive index values of these layers, right? It is not like they will be always constant. They will keep changing. When they keep changing, what happens? See, we are talking about a ray 1. Say for example, ray 1 is taking a particular path to reach the eye of the observer. But when the ray 2 is coming, from the same star, right? Since the composition of the atmosphere is fluctuating, it might not take the same path. It might take a different path. Means it will escape the eye. After some time, maybe another ray might travel in the same path and come and reach the eye of the observer. Which means what? Which means that due to the fluctuations in the refractive index of the layers of the atmosphere, right, what we'll observe is the light that is reaching the eye of the observer, right, will not reach regularly. It will be reaching only irregularly. So if we imagine we are seeing with our position fixed or static position, then the light rays entering into the eye from the star, because the star is not a large, it's a small object. Star is a small object, so we will not be able to consider a lot of number of light rays coming from the star. Because it is a small object, we will only be able to consider some small number of light rays coming from the star. And when they enter into the eye exactly, you will see that the observation will happen. But if they are missing the eye, means we will not be able to see the star. So because of this irregular phenomena, right, what we will see is that sometimes the light rays from the star will reach the eye and sometimes they don't. When they are reaching the eye, we will see that there is a bright observation that is made. When they don't reach, it is almost like what, invisible. So as a result, we will see this phenomena of twinkling. Okay. Now there will be another question. Why the same twinkling does not happen in the case of say sun, or when we are seeing a planet? Because some of the planets, right, we can see them in the night time. So why the twinkling phenomena does not happen for sun or moon? Okay, or even the planets for which we'll have a large view? Why the twinkling we will not be able to observe? Because the moon, right, we will see it like a large object. So here from the moon, right, we will not just have one light ray to be coming, we'll have many number of light rays that we can visualize to be coming because of the large size that we are able to see. So as a result, what happens is, for some time a part of these rays will be able to reach the eye, and for the other time they might escape the eye, but the other portion, right, they might now be able to enter the eye. So as a result, what happens is balancing out. Like star, because of the small size, we'll consider only one light ray to be coming, but a sun or a moon, because of the large size of the object we are able to see, right, we'll consider that there are many number of light rays coming. So some of them even they're missing, right. The average out phenomena, right, will be making sure that we don't see the twinkling observation. Now there can be another question: if we move out of the layers of the atmosphere, see for example the layers of the atmosphere are till here, if we move out, like we get into space, then we will not be able to see the twinkling of the stars. So if you go out of the layers of the atmosphere, right, and view the observation, like from a spacecraft or something, when we view the stars, there we will not be able to see the twinkling of the stars. Why? Because once we cross these layers of atmosphere, there will be no phenomena that will happen because of the refraction through the layers of the atmosphere. Okay, so this is about the concept of twinkling of the stars, which happens because of fluctuations in the refractive index values of the layers of the atmosphere. Okay, next, another observation with regard to this refraction through the layers of the atmosphere is the shape of the sun itself. Like if you look at in the early morning or in the evening, right, what we'll generally observe is, you can see in this representation. So what do we observe? We'll observe that the shape of the sun almost looks like what? An oval kind of a shape. Okay, so it looks like, flattened in terms of the height. So that is what we call as the oval shape. So why we will be able to see the oval shaped observation for the shape of the sun? The reason is again in the refraction through the layers of the atmosphere. So if you look at it, right, when we say early morning or in the evening, we are talking about the sun position being closest to the horizon. Okay, so here if you see the vertical diameter, we look at the vertical diameter of the sun, the ray coming from the top of the vertical diameter and the rays coming from the bottom of the vertical diameter. Okay, so different points of the vertical diameter, right, they will be sending rays, and these rays will get, like we'll have layers of the atmosphere, right. These rays typically enter it, they will not be entering at the same point, they will be entering at different positions in the atmospheric layers. So when they are entering at different positions in the atmospheric layers, their refraction phenomena will have a different course. All of them will not be having the same course of refraction. Imagine if all of them are having the same course of refraction like this, right, what we will see, that we will be able to see that the vertical diameter value will remain the same. What is the real value and what is the observed value? But since these rays are entering into the atmosphere at different layers, their refraction would not be identical. So if the light rays coming from the top of the vertical diameter, they are having a different kind of an refractive path. The rays coming from the bottom of the vertical diameter, they will have a different kind of a refractive path. As a result, what we'll see is that the you can say this is the kind of an object size, means the image size will be different. So the reason why we'll have flattening of the sun, or we'll say oval shape, is because the light reaching the Earth's atmosphere, right, from different parts of the vertical diameter of the sun will be entering at different heights in the Earth's atmosphere. And when it is entering at the different height, means it will be traveling through medium which are going to have different refractive indices. And when they are traveling through different refractive index medium, their path of course will be different. They all will not be having identical path, they will have different kind of path. Okay, and because they are traveling through a different kind of path, their bending will not be equal, it will be unequal bending. So as a result, what we'll see, the flattening of the sun, that will happen both during the early morning time as well as the evening when the sun is at the horizon point. Okay, so far we talked about the optical phenomena that we observe due to the refraction. Now we'll see the optical phenomena that we observe due to the total internal reflection. So which is what in short called as TIR. Sparkling of diamond, it is one of the very classic examples of the total internal reflection. So whatever the light rays that are entering into the diamond, right, henceforth they will keep undergoing total internal reflection. So the light will keep getting reflected inside the diamond, because diamond is what? It is optically denser medium, right? So the angle of incidence, if it is more than the critical angle, then the light ray will keep undergoing total internal reflection inside. As a result, we will see the sparkling of the diamond. Okay. The other very practical observation with regard to the total internal reflection is this mirage formation. The mirage formation, right, is also caused by the total internal reflection. Like, how do we observe the mirage formation? Like on a sunny day, if you are going on the road, you will see that at quite some distance on the road, there appears to be some kind of an image of the sky. We'll see that there is an image of sky. So the perception that we'll get is as if there is a water lying, because generally when we'll see the image of the sky on the road, when on the road there is a water, correct? So we'll get a perception that there is some water which is on the road, but as you move forward and reach that place, right, there will be no water. Okay, so this is a common thing that we'll observe. Even in the desert also you will be able to see that. Okay, so you'll get an feeling as if at quite some distance you have a water body or something, because you will be able to see the image of the sky, or whatever the things you will be able to see in the sand. So you will get a perception that there is some water body over there, but if you actually go there and check it, there will be no water body. Okay, so this mirage formation, how does it occur? If you look at the desert, or the situation where the earth is very hot. So when the earth is very hot, the layers of the air close to the surface of the earth will also be very hot. So because they are hot, what happens? The air molecules will try to escape away. Means the density there will be getting lesser. So the layers of the atmosphere close to the surface of the earth will be rarer, and above layers will be what? Denser, both physical terms as well as in terms of the optical phenomena. Now think about it. You have a tree over there. This is the object. The light rays coming from the tree. Now it's like what? They are coming from the denser, because above layers are what? Denser. They are coming from denser layers to rarer layers. So what happens? We will see that there will be what? Bending away from the normal, because when the light rays are coming from denser layers to the rarer layers, they will be bending away from normal. Now eventually you will reach some point where the angle of incidence will be more than the critical angle as the light rays are coming eventually, because as you come closer and closer, means what is happening? The density, optical density is keep on decreasing and the incidence angle is increasing. So you will reach a stage where the angle of incidence will be more than the critical angle. After that, what happens? You will see the rays will not enter any further below. They would undergo what? They would undergo total internal reflection. So the light rays will be bending onto the same side, and as a result, our eye will see as if the light ray is coming from a point over here. So this is what we will perceive as the image of the head of the tree. So this is a perception. Okay, so this is happening because of what? Total internal reflection. So as the heating of the earth in summer, or in the desert, when we have the air layers having different refractive index values. So generally the air near the surface of the earth becomes what? Lesser in terms of the refractive index. It becomes rarer. So the light rays coming from the head of the tree or something, they would at some point undergo what? Total internal reflection, and our eye will perceive as if the rays are coming from here. So the observation that we are able to see the head of the tree appearing on the surface of the sand, etc., right? What is the perception we'll have? We'll have as if there is a water body or something over there, because then only we will be able to see the image of the head of the tree inside the surface, right? So this is what we will generally refer to as the mirage formation. Okay, now there is an exactly reverse phenomena for the mirage formation, which we call as the looming. So looming generally happens in deserts during the night time. So when looming happens in the deserts during night time. So what is this looming phenomena? Night time, the earth will be very cool. Okay, so near the surface of the earth, the layers of the atmosphere will be denser. As you move to the upper layers means they will become what? Rarer. It is exactly the reverse. Now what happens? Imagine we have an object here which is on the surface. We have an object on the surface. Okay, so the rays coming from the object, now imagine what is happening. The rays are now coming from denser medium to rarer medium. So as a result, what happens? The rays will be bending away from normal. So the angle of incidence value will keep increasing. When we move from one layer to other layer, angle of incidence value will keep increasing. Eventually you will reach a stage where the angle of incidence is more than the critical angle. Critical angle either we will represent by theta c, or we can say IC also. Okay, so eventually we will reach a stage where the angle of incidence is more than critical angle. Then what happens? There will be the total internal reflection. So rays will come onto the same side. Now for the eye which is observing, right, it will appear as if the rays are coming from a point over here. This is the image. Like if you have an aeroplane, okay, here on the ground, then no, for an observer the aeroplane appears to be inside the sky. Okay, so this is what is the phenomena which is exactly reverse to the mirage formation, right? Mirage formation, what is it? You have a tree, the top of the tree image appears to be on the ground. Here it is the reverse. The image of an object which is on the surface, the image appears to be inside the sky. So what is the phenomena called as looming? So how do we remember it? It happens exactly reverse to that of the mirage formation. It will happen when? During the night time in deserts, because night time deserts will be what? Very cold. Now the other optical phenomena is scattering of light. Now scattering of light, people want to understand what is the difference between scattering of light and reflection. See, reflection means, see, you have a mirror, whether it is a plane mirror or a spherical mirror, which is typically a large object. It's a large object. When light rays are getting reflected, right, from a large object, that is what we'll generally call as a reflection. Okay, but what about scattering? If the particle size is very small, if the particle size is very small and the particles are encountering the incident light, so if the large object is encountering the incident light, that phenomena we call as what? Reflection. If small size particles, like the molecules or the ions, if they are encountering the light, then the phenomena that we'll observe in that case will be called as what? Scattering. So when the incident light is falling on a particles of small size, typically the molecular particles, etc., then we'll call it as what? Scattering. So here scattering is a little bit more detailed phenomena, because in our syllabus, right, we don't have the thorough study of the phenomena of scattering. But what we will look at is one of the simple principles of scattering, which is called as the Rayleigh principle of scattering. This is based on what we call as the elastic scattering of the light by the molecules. So for example, we have a molecule of a particular medium, so it can be even particles of the air. So when the light rays are coming and incidenting on the particles of the medium, the molecules, then here the Rayleigh scattering principle assumes that it is a elastic scattering. Elastic scattering means whatever the wavelength of the light that is incident, the wavelength will not undergo change. Elastic scattering principle is what? The wavelength will not be undergoing change. So there are other scattering theories also, like Raman theory of scattering, which is inelastic theory, but we don't need to go into all those details. So here this elastic model of scattering is sufficient for us. Now the light that gets scattered, typically, when we are incidenting light on the particles of the medium, the light that scattered, right, will depend upon the nature of the molecules. Nature of the molecules will mean primarily we are talking about the size. Okay, when the size of the particles is comparable to the wavelength, that is when we'll have more effective scattering. When the size of the particles is comparable to the wavelength, right, that particular situation will have more effective scattering of the light. But from the wavelength of the light point of view, generally the intensity of the scattered light, so we have the incident light and we have the scattered light. Okay, so the intensity of the scattered light is found to be proportional to 1 by lambda power 4. So this is as per the Rayleigh theory of scattering, which is based on the elastic model. Okay, so we don't need to get into the details of it, but this understanding is sufficient for us. What is it? The intensity of the scattered light is proportional to 1 by lambda power 4. Means what? When the lambda is higher, the intensity of the scattered light will be less. Means what? That particular light, so whichever is having a higher value of lambda, that particular light gets least scattered. Okay, so if you look at the visible colors, right, which is from violet, indigo, blue, green, yellow, orange, red, which has got the highest wavelength? Red has got the highest wavelength, which means what? Red gets least scattered. Which will undergo highest scattering? Violet will undergo highest scattering. So the observation is what? From the Rayleigh theory of elastic scattering, for the light which has got a lower wavelength, scattering will be more. For a light which has got a higher wavelength, scattering will be less. Now we'll see what is the reason why the color of the sky appears to be blue. So this is something that we'll observe when we see from the surface of the earth. What we'll see, the color of the sky will appear to be blue. So the reason for this is the particles of the layers of the atmosphere, right, the molecules or the atoms, they tend to scatter the light, because if you look at it, right, so this is violet to red, the lower wavelength that gets scattered most. So in the lower wavelength bracket, right, we'll have predominantly the blue. So the lower wavelength will get predominantly what? Blue color, and that gets scattered. Whereas the remaining portion of the spectrum, right, so if you have violet to red, means the lower part of the wavelength that gets scattered more. The higher part of the wavelength that will just directly reach the surface of the earth. So since we see that the scattered light, so we are here means we will be able to see what? The scattered light. So we'll see that the color of the sky appears to be what? Blue, because predominantly the lower wavelength region, right, that gets scattered by the particles of the atmosphere, molecules or atoms. Now again, if we move out of the layers of atmosphere, we go into space, then will this phenomena happen? No, right? Either we will be able to directly see the rays coming from the sun, or if we are on the other side of the planet, means we will not be able to see the rays coming from the sun at all. So which means what? The color of the sky, right, will not be having the blue when we move out of the layers of the atmosphere. So the color of the sky is blue only because there is an atmosphere around the surface of the earth, and because of the scattering of the predominantly blue color region, we will see the color of the sky appearing to be blue. If you move out of the atmosphere layers, means this phenomena, scattering, will not be there, and hence the sky color, right, will be the space color. Basically space will be what? Dark in color. Now similarly, when we look at the color of the water in the ocean, that also appears to be blue. Why? Because whatever the light rays falling, the particles of the sea, right, the small size particles, they also predominantly scatter the lower wavelength part, which is the predominantly blue color. That is the reason why we will also see the color of the water, sea water, to be blue. Now we would see that the danger lights or the indicator lights, generally the things that we want people to observe carefully, we will always give them the red color. Why? Because even so we see from a long distance, red light will get scattered least, because the wavelength is highest, right? So scattering of the red will be least. So we will see that the indicator light will be able to reach even longer distances without getting scattered. If instead you use a blue or some other color light, what can happen? The ray can easily get scattered. As it is passing through, the chances of getting scattered will be more. That is the reason why for these danger lights and indicator lights, right, we'll generally prefer using the red color, because it gets scattered least. Now even if you look at the color of the sun during the sunrise or sunset, it appears to be red. Okay, so at the midday time it will be bright white, but during the sunrise or sunset it will be appearing to be what? Red in color. Why? Because this is something that we already discussed in terms of the position of the sun when it is reaching near the horizon. But look at it, when the sunrise or sunset means we are talking about the sun position close to the horizon. So when you look at the path that the light rays actually travel when the sun is at the horizon, right, this will be the longest path. So we are the observer, we are here, it will be the longest path. When the sun is at the midday, right, it will be the what? Shortest path. So for an observer, because it will change from observer to observer, for any observer, right, the sun rays will travel through a longest path when the sun is at the horizon. So which means when the sun rays are traveling to the longest path, then predominantly what happens is all the other colors, they get scattered, leaving behind mainly red color, because red is the one that gets least scattered, right? Because if you have white, which is a mixture of all VIBGYOR, if all the other components are getting scattered, means we'll be predominantly having what? Red remaining. That is the reason why during the sunrise or sunset time we'll have what? The color of the sun appearing to be bright red. But in the midday means the shortest path, we'll see that the color of the sun will be what? Almost bright white. Okay. Now the other optical phenomena which a lot of us would be seeing whenever there is a rain happening, etc., is the rainbow formation. So what is the rainbow formation? It's something that we will be able to observe because of the mixed phenomena. Mixed phenomena means the light will be undergoing refraction as well as total internal reflection. So rainbow is formed because of what? The dispersion of light. So light gets dispersed. Dispersed means what? White light from the sun has to get dispersed. We'll see the spread of colors, right? So the dispersion of light that happens because of what? Refraction as well as total internal reflection that is happening inside the droplets which are present in the atmosphere. Generally when we want to observe the rainbow, right, like so if I'm seeing a rainbow on my front side, means sun will be on the back. So the observer, right, should stand with his back towards the sun. Like I'm standing here, I'm able to see the rainbow, means sun will be on my back side. Okay, so this is how, like you can see here, this is the rainbow. So what is it that we'll observe here? The red is the outermost, correct, and violet is the innermost. In this rainbow that you are able to observe here, what are we seeing? The outermost layer of the arc is what? Predominantly red. Innermost layer is what? Violet. Okay, so this is what we'll generally call as the primary rainbow. So obviously you will get a doubt. So what is the other rainbow? So the other rainbow will be called as a secondary rainbow. We'll talk about it. Primary rainbow happens because of, look at this, this is a raindrop. Let us consider it to be almost like a spherical. Let us consider the raindrop to be almost like a spherical. So sunlight, which is a mixture of all the VIBGYOR, will undergo a refraction first. Okay, here remember, when there is a refraction, violet will get maximum deviated, red will get least deviated. So you see here, red is here, least deviated from the original path. red is what? Least deviated. Violet is maximum deviated. It will come and it will incident here. So this is what? Total internal reflection. Okay. Then red will come along like this, violet will go like this. Okay. So this is the second refraction. So what you are the observer here, right? What you will be able to see? You will see that the red arc is at the top and violet is at the bottom, the innermost. So innermost arc is what? Violet. Outermost is what? Red. And what is the reason for the primary rainbow formation? 2 refractions and 1 total internal reflection. And here we are saying the primary rainbow is bright. This is in comparison to the other one. So what is the other one we are going to talk about? The other one we are going to talk about is the secondary rainbow. So secondary rainbow will be relatively dull. So comparatively the secondary rainbow will be what? Less bright. Primary will be what? More bright. Okay. So you can see here in terms of the pattern, right? For the primary rainbow, red is the outermost, violet is what? Innermost. Now when we are mentioning it these many number of times, by now itself you would have got an idea. What is it? In the secondary rainbow, the pattern is going to be reverse. So what is secondary rainbow? This is also something that we'll see. Like, sometimes secondary rainbow will not happen very regularly. Secondary rainbow happens in very rare cases. Okay. So very rarely only we'll be able to see it. So you see here, this is what? This is the, so red is the outermost. And here somewhere we'll have the violet, innermost. So what is this? This is the primary, bright. But you see here there is one more rainbow form and the pattern is exactly reverse. You see what? Red is what? Innermost. And violet is what? Outermost. Not only the pattern is reversed, we will see that the secondary, this is what is the secondary. This is what? The secondary rainbow. Secondary rainbow, not only that the pattern is different, but the secondary rainbow is also what? Dull. You can see. We'll see what is the reason for the formation of the secondary rainbow. So secondary rainbow, right? There are, different ways of understanding the formation of the secondary rainbow, but one of the simplest approach is from what we have learned already in terms of the primary rainbow formation. Okay, so we have the primary rainbow formation. Already we have seen this, right? What is the primary rainbow formation? Sunlight, which is a mixture of violet to red, will undergo refraction once, then total internal reflection, then refraction twice. Okay, so you will see that what is the, so we are the observer means we will see that red will be the outer layer and violet will be the inner layer. Okay, so this is what is the primary rainbow formation, which happens because of what? Because of 2 refractions and 1 total internal reflection. Okay, now we look at what about the secondary rainbow formation. So from here onwards, right, instead of undergoing the refraction here, if it is undergoing a total internal reflection, so this is TIR1, this is refraction 1. Here we will say TIR2. So the red will go like this. Now it will undergo refraction. Okay, this is the red. Same, the violet also will undergo the second total internal reflection. So from here it will go like this. Okay, so it will go like this and it will come through a path. So what you see, you are the observer here, means what you will be observing here, you observe that the violet will be what? The outermost layer, and red will be the innermost. So it is just reverse to that of what we have seen in the case of the primary rainbow. So here what is happening? 2 refractions and 2 total internal reflections. The innermost will be what? Innermost arc is red, outermost arc will be violet. Okay, and since it is undergoing the total internal reflection twice, there will be more amount of absorption of the light component. As a result, the secondary rainbow will be generally considered to be dull. So the more scope for the absorption of light will mean what? The final rainbow that is formed is what? It will be less bright in comparison to the primary rainbow. Okay, so this is about the difference in terms of what is the primary rainbow, what is secondary rainbow. Not only that, if you look at the angle, like say for example we are looking at the angle that the rainbow is observed with respect to the horizontal. Typically the primary rainbow, right, will be somewhere around 42 degrees, and the secondary rainbow will be close to 52. Okay, so the values might change a little bit depending upon some other considerations, but typically they will be what, the primary rainbow will be around 42, and secondary rainbow will be having a higher angle, so it will be making a higher angle with respect to the horizontal, like we have seen in the diagram also, right. Secondary rainbow will be happening at a higher angular formation. Okay, so this is about the two types of rainbow that can be formed. One is the primary rainbow and second is the secondary rainbow. Okay, so these are some of the effects of the optical phenomena. So we talked about the effects due to the refraction of light and effects due to the total internal reflection, and then also we talked about the effects due to the scattering of the light. Okay, so this will sum up what are the effects due to the optical phenomena, and we'll see in the next video.